So I'm going to be talking about some work in mass timber that we've been thinking about in my group for quite some time, and specifically just because this isn't really as much of a technical talk as you would do at a conference. It kind of gives me an opportunity to talk about this idea of creativity and what we can think about in the future. It also gives me an opportunity to lay a little bit of background in terms of history. So for those of you who know where I started, I think you would consider me a ride and die steel person. And I was lucky enough to have the opportunity to work with Steve Mahan as my advisor. And I just want to say, when it comes to creativity in structural engineering, he really stands out. This sort of image on the right is actually, I took this picture. It's an image I have on my wall of my office. It was sort of a collaboration between me and Steve. You see some of his drawings on there, some of my drawings, a little bit of my scribbles, a little bit of his scribbles. And I just want to say that this is a man, you would walk into his office with an idea, and you would talk about everything else but the idea you walked in with, and about 10 other new ideas that were the most brilliant thing ever. And so I don't get much of an opportunity to talk about him, so I really love that I get to talk about this at this Bloom Center meeting, and specifically dedicate some of the work you're going to see here to his ideas and his inspiration. So I'm going to call it the Steve Mahan effect. You'll see in our lab we do a lot of different things, and a lot of it is sort of this effort to look at creativity and structural design from a different lens. So Akiri Seki's in the office. He does a lot of work on the offshore wind side that we've been doing a lot of different studies in. Gustavo Rojo is also in the audience. He does some of the work, as well as Shan Razi does a lot of work with accelerated computing and real-time simulations. Given that this is a sort of a Bloom event, I'm going to focus on this first piece. Classically in structural engineering, we've thought a lot about earthquake engineering, but I think we all know that's starting to shift a little bit. Firstly, in terms of more hazards, and secondly, in terms of climate change. And so I specifically just want to focus this on the creativity we can sort of ground in maybe some traditional ideas, and sort of broaden our scope as well. So, classically, we've been hearing a lot about this in terms of the talks today. We've been really focused on experiments and testing for life safety and collapse prevention. This was a test done, again, this talk is going to be geared a little bit towards mass timber, done at UC San Diego, and by John Vandelin as part of the Nice Soft Wood Project, and, very dramatic. I want to say this was like the 10th shake that they did, and they were trying to collapse it. But I think it points out sort of an interesting piece, is that a lot of our research in the experimental realm has really focused on what is the existing building stock like? How do we design right now? And then what does that damage mean? It focuses a lot on the damage piece. So I think what we're seeing, and you can see that from a lot of those talks, is what happens, yes, the damage piece is very important, but how do you also start thinking about things like resiliency and of communities, functional recovery? You could throw affordability in there as well, in terms of the housing stocks as well as the socioeconomic makeup of a community. So that's giving a lot of sort of resiliency objectives to now define our building. So instead of just aiming for life safety and collapse prevention, we have many more metrics that we might be interested in, combined with sort of carbon emissions, greenhouse gases, the effects of climate change. There might also be some more sustainability metrics that we might want to think about. And so I started sort of piecing this together in my head about how this relates to creativity in our own design processes. And we're dealing with significantly more metrics than we've really had to design for before. And not all of them are aligned. Oftentimes they're conflicting. And so this was sort of an idea of mixing and matching that I actually got from a number of discussions with David Marr, where it was kind of this idea, we have all these objectives. Maybe instead of just having one seismic force resisting system that's somehow magically able to meet all of them, we start thinking about all the data we have, the well-established devices, the different structural systems, and start mixing and matching them to actually tailor our designs to meet very specific performance goals depending on what you want. And so I think there's some concepts in here that could be quite interesting in terms of thinking about creative design. So what's needed to do this? And I'm going to be a little bit tongue-in-cheek here. What's needed to do this is a lack of resistance. And what I mean by that, the reason I'm choosing mass timber for this talk is it's not really quite yet codified, and so there's not a lot of momentum behind it. It's the wild, wild west. They're allowing us to do whatever we want and propose whatever we want, which has its advantages or disadvantages. You can look at it in many different ways. But it allows us to propose things maybe in terms of this mixing and match archetype that really is very difficult to propose in things that are already ingrained and codified and have a lot of significant mass to change. And so I'll sort of tailor this talk specifically around this idea of using mass timber as sort of a playground where maybe some of these ideas can then propagate to other building materials and structural systems. So that's not the only thing, that resistance piece is not the only thing that would be needed to sort of propagate creative design. It needs to be really well grounded in the literature and I think well supported in practice. So a lot of my work in steel systems was not just the work that I was doing as part of my research. It was also sort of being caught on by engineers and industry. So you'll see this is the image of Greg Luce design for the Tesla Gigafactory. You'll also see some work from Tipping at the top, and I think Leo was in the audience as well. And so this is really important to have the ideas actually get entrenched and to make change. The other thing is you really need to understand the behavior not only of the materials and components, but of what this is combined as a sub-assemblage and structural system and how it holistically acts as a unit. You need to really understand actually the dynamics of the system, what goes beyond sort of traditional testing and sort of looking at it in terms of shake table, dynamic response. And then finally, you need to do that not just for maybe a 10-story building, but also for a 6-story building, which I'm going to sort of talk about in this presentation as well. So you need to know that dynamic response for multiple building heights, multiple story numbers, and ideally for different types of irregularities. And then ultimately look at that in terms of the design with numerical models where I believe the real creativity comes in. And if you can get these first 3 pieces, then you can start really playing around numerically and coming up with something that maybe hasn't been seen before. And so I can't talk about all of these different pieces. Different people in my group have done a number of things on each one of these categories. But hopefully I can sort of gloss over a few and sort of focus on those last 2 a little bit. So let's talk about inspiration from the literature and practice. So I think the rocking wall concept is not new. You've seen it a lot in reinforced concrete. Craig Dearline has done a number of different projects in terms of rocking braced frames. There's been some work by Liddell Weeb up in Canada also on this topic. Lehigh University has also studied it. So it made sense to sort of ground some of this work in mass timber, thinking about post-tension, self-centering rocking walls, replacing the rocking wall component instead of a steel braced frame or a reinforced concrete shear wall, replacing it with something that's either CLT or mass ply panel, some sort of mass timber product that has enhanced stiffness and strength characteristics. There's also inspiration about sort of these pivoting type systems that I like to say are sort of in the same family as the rocking system. So the pivoting system sort of has a pin at the base. It's sort of background, and there's sort of the strong back system that I was doing with Steve Vahan. There's also some sort of similar work by Robert Tremblay in terms of the tied eccentrically braced frame. But the same concept, except, you know, in this case, instead of rocking and uplifting at the base, you have some sort of pin-based connection. But instead of a brace frame or a concrete frame, or a concrete wall, you could replace that with, say, this mass timber product. And the idea of mixing matching then really comes into play. And so you can say, okay, so we replace the wall, the elastic component in these systems with mass timber. We gain some advantage in sort of aesthetic properties. I'm going to limit myself a little bit when I say potentially sustainability properties. It depends kind of on how you slice those numbers. But then you can combine them with something that's fairly well established. In this case, we were using buckling restrained braces, but we call them buckling restrained boundary elements just to have the same acronym. But then you can have the stable energy dissipation capacity of the braces sort of involved in this as well. So Gustavo, who is also in the audience, this is our phase 1 of this system. So we designed and tested a 3-story version of this up at Oregon State University. I don't have time to really go through all the details, but something I just want to point out about it is that this particular system had a lot of details that were the most of our time trying to figure out. And because of the lack of self-centering capability, also had residual deformations in the BRBs in this case, which means that if you think about in a static case, this system unloading and reloading with the same initial stiffness, you can get a lot of residual deformations in the BRBs that make it sort of not quite easy to repair after significant shaking or significant drifts. I should also say there's a caveat here. For a dynamic analysis, this might look a little bit different and not as severe as what we did in terms of the testing program. So this was sort of conceptually the idea. Can we sort of look at these systems in terms of mass timber components with well-established energy dissipators that are coming out of the steel world? We modified it somewhat to then start addressing the residual drift component. And so, we had this pivoting system on the left that was sort of the original, call it phase 1 of this hybrid wood-steel system. And then the figure on the right was, well, let's add post-tensioning that enable self-centering and mitigate residual drifts after a seismic event. And so it was just easier for us to sort of balance the overturning moment from the BRBs if we were to actually allow it to rock in this case. And so in this case, we went from a pivoting system in phase 1 to this sort of self-centering rocking system in phase 2. And we had the opportunity to actually test this in a 6-story version of this at the UCSD shake table facility. So this was, again, Gustavo's design. Huge shout out to him on this. And then Morgan McBain, another one of my students, actually led the testing program itself. And just to wake everybody up a little bit, I think there's sound.
There's 100% actually.
So this is a maximum considered earthquake event using the 1994 Northridge earthquake. And it's very loud. Pretty short earthquake. But was tested in 3 degrees of freedom in that case. I cut out my expletives for that particular video. It's rather scary being there in person, especially when you actually see your design tested. But what's interesting about when looking at this dynamic response, so this particular building, if you combine it with the 10-story experiment that came before, we actually removed the top 4 stories to make it a 6-story experiment. And then we tested a variety of different lateral system designs, all of which were rocking, but this was the only one with the BRBs. What was interesting about it is that it survived about 150 shakes, ranging from service level to beyond MCE. This particular system that we were looking at experienced 23 shakes, 18 of which were conducted by us and another few of which were conducted for the shake table tuning. And here's the results of this. We tested everywhere from with 4 different ground motions, from service level again to beyond MCE level events. And the drifts, even after about 1.1 MCE using that Northridge ground motion, which by the way is a pretty severe ground motion when you scale it up that high, had pretty minimal residual drifts, completely repairable after the event. The thing that's maybe a little bit interesting about it is that there was quite large accelerations that tend to increase as the intensity of your ground motion increases. And that's sort of one of the aspects of these rocking or pivoting systems that you do need to think about. They tend to exhibit large acceleration effects. Which leads me to this sort of one of the last pieces. This was some testing that we did in collaboration with a number of U.S. institutions and also with the Japanese at the E-Defense Shaking Table Facility. Brian Massadio, also in the audience, was the student working on this project. And in this case, there was a number of hospital components distributed in the building. And this isn't quite the same as the mass timber system, but it has sort of that pivoting spine, this time made of steel. I want you to look at the difference between the uppermost videos and the lowermost videos. The uppermost videos is just sort of the raw action of that pivoting spine. The lower version is us adding higher mode mitigation. Again, just adding more components to the system in this idea of mixing and matching. And you'll see quite a difference in terms of the non-structural response. So you can see very large higher mode accelerations that are tending to be exhibited in the upper video. And you can see that that's pretty well mitigated by the lower videos. Keeping in mind that most of the non-structural components you're seeing here are actually designed to withstand pretty high Gs. So, just something to think about. We managed to have almost negligible residual drifts, but on the non-structural side, that's something that still needs to be considered. So that brings me to this last piece. So this is a diagram developed by one of my students, Morgan McBain, and I think we all have seen the performance-based design integrals many times, and so I think that's something that we're very familiar with. So when we think about having well-established numerical models that are grounded in this physical testing data, and then adding in sort of this component of, say, life cycle assessment, we've been sort of trapped into thinking about this design as a forward analysis kind of design. So you have some sort of location, you have some sort of design at that location, you check its loss in terms of deaths, dollars, downtimes, or if you prefer, serviceability, sustainability, and safety. And then you could potentially check it in terms of a life cycle assessment to look at greenhouse gas emissions, embodied carbon, et cetera. But what we're starting to think about is, well, if you have enough data to build models that you can actually walk backwards from, perhaps what you can instead do is start at the metrics, say these are the metrics I want, and again, potentially they're competing a little bit, and then walking backwards to give you a potential design space of what that might look like that you can then choose from. And so this sort of leads me to this last piece in rounding out this presentation when it comes to creativity and design. I think we need to change how we're thinking about structural engineering. And what I mean by that is, we have engineers' time on the y-axis, and typically we have sort of this concept, creativity, and innovation on the left, design and analysis in the middle, and then interpersonal communication and engagement on the right. And very classically, we've been sort of spending a lot of time in this middle part. And I think the reality is that that's not going to be the case for very much longer. And that means we need to figure out where to spend our time in maybe these other realms. And so I just want to sort of end on this idea of what the future generation is going to have to contend with as they have more data, faster models, and more design choices that they have to do less of this middle piece. And what that means for us when we think about structural engineering as an industry. And so with that, I'll just end with this final slide and the many students who have been so fantastic as part of this work. There's a few of them not in the photos, not because I don't have photos of them, but they weren't at these particular conferences. So unfortunately, they didn't quite make it in there. But I just want to say that they're a fantastic group, and this work could not be done without them. Okay, thank you.